So, I am Rachael Livermore. I am an astrophysicist at the University of Melbourne, and I'm going to talk tonight about magnifying the distant universe. If any of you are tweeting, is my Twitter handle there. You may notice that my title slide matches my dress. So this is some of the galaxies that I actually work on in real life. I make them into dresses so that when people come up to me at conferences and say, "Oh, I didn't make it to your poster," I can go, "No need." So why do we want to look at the distant universe? The very simple reason is that things happen in the universe on really, really slow timescales. Like things I look at, we're talking billions of years, and PhDs don't last that long. So when you want to figure out how you get these galaxies into the kinds of shapes that we see today, you can't watch one galaxy and watch it evolve. You have to look at galaxies of lots of different ages and figure out how that forms into some kind of evolutionary progress. So it's kind of like having a bunch of photographs of babies, children, and adults and figuring out how you get from one to the next. And luckily we can do this because if we take an image of space, this image is completely full of galaxies. Every little speck is a galaxy with hundreds of billions of stars. The further away we go, the longer it's taken light to reach us. So as we get here, you might notice that all of the big yellow and orange things have sort of vanished. This is because there's an evolutionary change in galaxies at this time. We're about halfway back to the Big Bang. And at this time, there are a lot more new young stars being formed. And young stars tend to be blue, hence the galaxies look blue. You also don't see a lot of grand design spiral structures in this epoch because they haven't formed yet. There's a lot more irregular things, a lot more mergers going on. And as we get further back still, the galaxies are going a bit green. This is not a real thing. They're still forming stars, but the universe is expanding and that blue light is being redshifted. And then eventually we get back to this point where it seems like there's nothing there. Now there's two possibilities here. Either there are very, very few galaxies at this point. We're now maybe 1 billion years after the Big Bang. Or the Hubble Space Telescope isn't quite sensitive enough to see them. And so this is the epoch that I study. I want to look at the baby pictures of galaxies and figure out how they formed into what we see around us today. And so I want to look at this region right at the end there, where galaxies are tiny little specks, and there aren't very many of them, because apparently I like to make life really difficult for myself. So how do we do this? Well, there's two options. The first one is telescopes are essentially buckets for light. Now, if you want to collect rain in a bucket and you want more rain, you've got two options. You can leave your bucket outside for a really, really long time. Well, that's what that video I just showed you was. That's the Hubble Ultra Deep Field. And that's about a month of leaving your bucket out in the rain. Or you can get a bigger bucket. So this is something we're working on. And these are our bigger buckets that are in the pipeline. The one on the top there is the James Webb Space Telescope, which I will mention very briefly at the end today. And also the Giant Magellan Telescope, which I'm not going to talk about, which is a ground-based massive telescope being built in Chile at some point in the next decade. I've learned not to put dates on telescopes that don't exist yet. But the James Webb Space Telescope, incidentally, does exist, but it's not in space yet. So these are obviously decades-long projects to make these new telescopes. And again, PhDs don't last that long. It took me 4 years to get my PhD. Can't build a telescope in that time. So I cheated. And how do you cheat? Well, that's what I'm going to talk about. It turns out the laws of physics are contrived to allow us to use dark matter as a gigantic telescope, which is weird, right? So to understand how this works, we need to turn to Einstein, and specifically Einstein's theory of general relativity. Don't go to sleep yet. This is really cool, I promise. So Newton had some laws of motion which work very well, but they treat space as an empty arena in which stuff just happens. The difference with Einstein is Einstein said, what if space is not just an empty arena? What if it's an active participant in the universe? So in the absence of matter, space is flat, and anything moving through that space moves in a straight line. But as soon as you introduce something that has mass, and mass curves the space around it, so now anything moving through that space is going to follow a curved path. Now, the thing represented by that yellow line could be something else that has mass. So an obvious example is if our star there is the sun, the Earth moving through the curved space around the sun thinks it's going in a straight line, but is going to go around in a circle, and this is how we have orbits. But this is also true for light. If light moves past something that has mass through curved space, the path of the light gets curved. So when this was originally realized, it was thought of as not useful or interesting in itself, but a kind of useful test to see if general relativity is real. So one way that you can test general relativity is you look at a bunch of stars. Now, ordinarily, when we look at stars, we look at them at night. And what that means is we're looking away from the sun. But if you wait 6 months until the sun is in between you and those same stars, then now the light from those stars has had to go past the mass of the sun, where the space is curved. So we introduce the sun in the middle here. Those stars will appear to move out from the sun. Now, of course, the reason you can't do this every day is the sun is really bright, and you can't see stars during the day. Except sometimes, when can you see stars during the day? Solar eclipse. So we introduce, someone messed with my slides. Pretend the moon's in front of the sun. When you have a solar eclipse, you block out the light from the sun. You can now see those stars, but now the light has had to go past the sun, and so they're in a different position. So this was tested with a solar eclipse in 1919. Eddington led a team to a little island off the west coast of Africa where there was a solar eclipse, measured the positions of stars, and led to my favorite headline that has ever been published in the New York Times: "Lights all askew in the heavens. Men of science more or less agog over results of eclipse observations." Now, whenever I show this, I like to say the women of science knew exactly what was going on. My favorite bit: stars not where they seemed or were calculated to be, but nobody need worry. So this was really great as a test of general relativity. It proved that general relativity was real. At least it made a testable prediction that was then tested. And it made Einstein a celebrity. Within a few years of this observation confirming general relativity, there was something like 100 books about relativity, and this is basically why you've heard of Einstein. But as for it being useful, that wasn't something anyone really thought about until this dude came along. This is Fritz Zwicky. By all accounts, quite a character. Someone that I know holds this guy single-handedly responsible for the complete lack of progress in cosmology between about 1930 and 1960 because no one wanted to work in the same field as him. I would like to tell you things have changed, but no, those people still exist. What I've heard, though, of people who actually worked with him is he was an asshole to his peers, but was generally nice to people beneath him, like students. So in my book, that's pretty cool. So he had some cool papers in the 1930s. Don't worry, you can't read this. I'm going to read it out, the important bit to you, where he talked about using nebulae as gravitational lenses. Now, if you've heard the term nebula before, he's not talking about what we now call nebulae. He's talking about galaxies, which at the time were known as spiral nebulae. And there's a key phrase in here where he talks about nebulae being far more useful than stars to use as gravitational lenses because they have a lot more mass. A galaxy is made of billions of stars, therefore has more mass than a star. And most interestingly, he says, if you could look at things that were behind these galaxies, they would be magnified because of the distortion of light, making it act like a lens. And therefore, you would be able to see things that are way further away than you can see otherwise. And this was published in the 1930s. It was kind of ignored. One of my favorite plots to look at in science is the citation record of this paper. It's like 0000 for 50 years. And then what happened in the 1980s? Digital cameras. So once digital cameras, CCDs, started being fitted to telescopes in the 1980s, and we had the extra sensitivity, it turned out you really could see these galaxies behind other galaxies that were being gravitationally lensed. So why does this magnify the light? Well, this is really cool. Let's pretend that the Whirlpool galaxy is super far away. I mean, it's like 60 million light years away, but to me that's not very far. If you put a cluster of galaxies in between us and the Whirlpool galaxy, it bends the light like this. So where ordinarily the light would go off in all directions, now some more of it gets focused towards our telescope. And this has two effects. First of all, in my super technical diagram here, you've got more yellow lines going into our telescope. That equals more light. So we've made our bucket bigger without actually doing anything. But secondly, they're coming from different directions. So you actually get multiple copies of the same galaxy observed in different places across the sky. Super weird, right? But really, really cool. So to give you an idea of what this would look like, let's take our same Whirlpool galaxy, put it behind our galaxy cluster. Now, in the lower right down here is where the galaxy really is. And we're going to move it behind the cluster. And you can see it moving along at the top there and then there. There was a tiny, brief moment where it made a gigantic arc across the sky. And in that brief moment, if it happens to be located in exactly the right position behind our galaxy cluster, it's huge, so much easier to see than it would normally be for a faraway galaxy. And that means we're getting more light from it, we're more likely to detect it, but also you can see inside in way more detail than you can normally, which is really cool. So this image here is a real galaxy cluster. It's called Abell 2744. It's also featured on my dress. And this was part of the Hubble Frontier Fields program, which is what I've been working on for most of the last 5 years. This was one of the largest programs ever undertaken with the Hubble Space Telescope, and it was looking at clusters of galaxies with the specific aim of finding these distant, faint galaxies that lie behind them. So this is our image, our up-to-date Hubble Frontier Fields image of the same cluster. And you can see there are some kind of stretched out shaped things. These are lensed galaxies which are not part of the cluster, which are behind it and have been magnified. Anything you can see in the image, though, is way too close for me to care about it. What I care about are things like this. Tiny, tiny little specks. But these are galaxies seen only a few 100 million years after the Big Bang, in the very, very early universe. And the only reason we can see them is because they've been magnified by the distortion of space around this galaxy cluster, which is mostly the dark matter in the cluster. And these might not look like much, but to me, these are super booming bright galaxies, way brighter than you can normally see in that region of time. So we had a press release out about this about a year ago, which I'm sure you all saw. This resulted in us being able to find the faintest galaxies in the early universe, which is pretty amazing. And although we do have these new telescopes coming up, this isn't going to invalidate what I've done. It means I'm going to use the same technique, but with a new telescope and go even fainter and even more distant, which is pretty cool. So this is the magnifying effect, but I also mentioned you get multiple copies of the same galaxy. So I wanted to show you this cluster because it's really, really cool. It's also on my dress. This is MAX 1149, featured in 2 chapters of my PhD thesis, and then after that was also observed as part of the Hubble Frontier Fields program. And it has this cool galaxy, which is cool because you can see that it's a spiral, and it has 3 copies. There's 3 images of the same galaxy seen at different points throughout the cluster. And it just so happened that when the images were taken for the Hubble Frontier Fields program, a supernova went off in this galaxy. So you can see in this blown up thing here, you can probably see 3 specks of light. There's actually 4. You can only just see the one at the bottom. These were not there when I took the images for my PhD. When we went back for the frontier fields, there were these new specks of light. This is a supernova, a star at the end of its life that's exploded. And because there's 3 copies of the galaxy, you can work out the different amounts of time it takes light to reach each of those 3 images. And you can say that one at the top left probably got there in about 1995, so sadly we missed that. This one happened in 2015. And then the one in the middle was predicted to happen somewhere between 2015 and 2020. And it turned out that in December 2015, it did indeed go off in the 3rd image of the galaxy, which just goes to show science actually works. It's pretty amazing. And so, as I said, the next big development is going to be the James Webb Space Telescope. Was originally due to launch ages ago, for a long time was due to launch in October of this year. The latest official news is probably 2020. Rumors are putting it later than that. But if it ever launches, it's going to be amazing. And this is why. Hubble is on the left there. And you can see just from the size of the mirror, this is a much bigger bucket. And the tiny little speck over on the right there is the current best space telescope we have that works in the infrared. So to show you what a difference this is going to make, we look at our Whirlpool galaxy as though it was very, very far away in the ultraviolet and in the optical. This is the best we can do currently. This is what it looks like. If we do it with the James Webb Space Telescope, it looks like this. So this is going to be a complete revolution in what we can do with the distant universe, which is pretty amazing. Now, before they take the microphone away from me, I want to plug something. As well as being a nerd, I'm also a nerd. So I enjoy science fiction films, but I enjoy them even more if I get to ruin them for other people. So I run a series at the Cinema Nova in Carlton called Big Screen Science, where we show a science fiction movie and then I tear it apart. So yesterday we did Apollo 13, which is really fun. The next one of my all-time favorites, Star Trek II, The Wrath of Khan, is going to be on Sunday, July the 8th at 3:30. It's really good fun. You should come. You can get tickets on the Cinema Nova website. So I hope to see you there. So with that, I will say thank you very much.
Go to nerdnite.com to find a Nerd Night event near you. And don't forget to subscribe to our channel for our latest presentation.